is our project focus on develop an automatic DC motor speed control system which aims to ensure consistent and efficient motor operation under varying load conditions. PID control is used to maintain a specific motor speed RPM by continuously adjusting the control input based on real-time feedback. Real-time feedback is obtained from an encoder that measures actual motor RPM, providing precise and updated information required for accurate speed regulation. The PID algorithm adjusts the PWM signal to minimize the error between actual RPM and set point, ensuring the motor speed remains stable and responsive to change. The last one is the system can control both forward and reverse motor rotation based on the PID output, allowing for flexible operation in application requiring bidirectional movement.
I will explain the function of all components that we have used. First is Arduino Uno, the brain that controls our project. Next is junction box, to protect and organize wiring neatly to make the project safe and tidy. Next, L298 and motor driver dual H bridge act like a bridge between Arduino and motor, allowing small signal to control bigger motor power. DC motor with encoder convert electrical energy into mechanical rotation, while propeller create thrust by pushing air when rotated by a motor, allowing movement. Jumper wire connect all components. Breadboard connect 5V and ground easily to different components, help organize the circuit. AC to DC adapter change AC power into DC power. Next is DC jack barrel, allow to plug adapter easily. Next, I will explain about the wiring. This circuit use Arduino Uno and L298 and motor driver and a DC motor with encoder to create a closed loop control system. The Arduino controls the motor speed and direction using PWM signals, while the encoder gives feedback to adjust speed using PID. A breadboard distributes power and all grounds are connected for stable operation.
The functionality for this project is a DC motor speed control system using PID and encoder feedback. The goal is to maintain the desired RPM by automatically adjusting the motor speed using the PID algorithm. It is both forward and reverse direction depending on the PID output. All key data including the actual RPM, PWM output and set point are monitored in real time using the serial plotter and serial monitor. The system updates every 40 milliseconds to ensure accurate and responsive control performance. In this graph, we show the system response when a set point of positive 150 RPM was applied. As you can see, the green line is the set point, the blue line is the actual RPM from the encoder, and the orange line is the PWM output. The motor rotates clockwise, and although there was some small overshoot and oscillation at the beginning, the PID control managed to stabilize the speed close to the target. This provides that the PID control is working to reduce the error and keep the motor steady. Next graph shows the system response when we apply a set point of negative 150 RPM. This causes the motor to rotate in the counterclockwise direction. Again, the blue line shows the actual RPM going toward the negative set point, and the orange line is the PWM. Now, going negative to reverse the motor. Although there are small fluctuations, the system successfully stabilized near the set point. This means The same PID setting are effective for both forward and reverse rotation.
Now, I will explain the discussion based on our project result. Firstly, our project provide precise and stable speed and direction control, ensuring that the motor perform accurately across various applications. The system continuously compares the set point against the actual speed using encoder feedback, allowing real-time adjustment to maintain consistent operation. In terms of control component, the professional component give a quick response to any speed error, helping the system react immediately whenever there is a deviation. Moreover, the integral component remove steady state error by correcting long-term mismatch between the set point and the actual speed. In addition, the derivative component reduce overshoot and oscillation, resulting in a smooth and more stable motor behavior. As a result, the system is able to maintain the motor speed even under change load, which is ideal for robotics and automation, whereas consistent performance is critical even with sudden change in resistance or operation condition.